We are going to start talking about limits today. We, of course, do this for functions of real numbers, real valued functions of real numbers. So let the function f of x be defined around a point A. What does it mean around A? That is, f of x is defined for all x, for all x in some open interval in the form a minus h to a union an open interval of the form a to a plus h for some positive h. So this is what we call formally in mathematics a deleted open neighborhood of the point A. So the point A itself is not included. So we take a point A minus h, a plus h. So the function should be defined on both sides of the point A. And it may be a very small interval, as long as it is an interval, as long as the number h is a positive number, we can talk about the limit of the function at the point A. This is called a deleted open neighborhood of A. Deleted because we take out the point A itself. All right. So probably you heard about limits before. Here we will try to give a more formal and maybe a little bit more detailed discussion of it. Now, what we mean by the limit of f at the point A is about how the function, how the values f of x for a particular value of x, f of x is a value of the function. So how the values f of x behave as x takes values getting closer and closer to A. Of course, this is a very intuitive sentence. It's not mathematically precise. Before the end of this chapter, we will try to make this definition precise, but for the moment, we are going to consider some examples. So in the first example, this is a classical example. This is how we always start discussing limits. Consider the function defined by x squared minus 1 divided by x minus 1. So this is the definition of the function f. Okay, so with this definition, x is not defined at the point x equals 1. Because x equals 1 makes the denominator 0. Yes, it also makes the numerator 0, but as long as the denominator is 0, the value doesn't belong to the domain. So the point x equals 1 doesn't belong to the domain of f, but it is defined everywhere else. So I'm going to talk about trigonometric functions. First, I want to talk about limits a little bit, and then I will come back and talk about trigonometric functions when we start discussing trigonometric limits, okay? So the point x equals 1 is deleted, but it is defined everywhere else. Okay, so what is the limit? Okay, for x different from 1, right? If you consider the values of x in the domain of f, we can write the function as the numerator can be factored out as x minus 1, x plus 1. So as long as x is not equal to 1, we can simplify the factor x minus 1 and say that f is equal to x plus 1. But this is only for x different from 1. 1 is not in the domain. So if you consider the graph of this function, 1, 2, this is deleted. And then when x is 0, it is 1. So this is the graph of y equals f of x. So we can see intuitively that as x gets closer to 1, the values f of x gets closer to 2. So we say that the values f of x approaches 2 as x approaches 1. And we write f of x approaches 2 as x approaches 1. So we say that this function, although it is not defined at x equals 1, it has a limit at x equals 1, and the limit is 2. So limit of f of x at x equals 1 is 2. And of course, instead of writing this whole sentence, we just write limit as x approaches 1 of the function f of x. Remember, f of x is x squared minus 1 over x minus 1, and this limit is 2. We see this limit as, you can say we studied the graph, we see that the function, the values of the function approaches the number 2 as x approaches 1, and we say that the limit is 2. And similarly, by just considering the picture, the graph of the function, we can get some other simple limits. Any question on this example? Example 2, we can see that for any real number a, this is element for any real number a, if you take the limit as x, for the limit, sometimes I write this curly L, sometimes the straight L. I hope it doesn't confuse you. The limit as x approaches a of the function x. If the function f of x is equal to x, of course, this limit is a. When you consider the graph, y equals x, as x approaches a, the values of the function also approaches a. And another simple limit, when you take the limit as x approaches a of the constant function. Let's say your function is constant at some constant c, and limit in this case is, of course, again, this constant. So in this case, our picture is, we have some constant c, the function is constant. So as x approaches a, all the values of f are constant anyhow. So the limit of the constant c is again c. Okay, so as I said, the limit is about the behavior of the function for the values of x near a, but not at the point a. So as another example, if you consider the function, partially defined function, let's say it is x plus 2 if x is not equal to 3, and it is minus 10 if x is equal to 3. So the graph this is the graph of the function. For x different from 3, it is given by the function x plus 2. But when x is equal to 3, the value is defined to be minus 10. But when we are looking at the limit of the function as x approaches 3, we are looking at the limit of the expression x plus 2. So we don't care that at the point 3, the function is defined to be minus 10. We look around 3, and around the point 3, the function is defined to be x plus 2. So for the limit, we take the limit of x plus 2, so the limit is 5. Okay. So with this example, and also the same principle applies in example 1. In example 1, at the point 1, the function is not defined, but around the point 1, it is x plus 1. So for the limit at 1, we are in fact taking the limit of x plus 1. So the same principle here, at x equals 3, the function is minus 10. But around 3, it is x plus 2. So for the limit, we look at the expression x plus 2. So I'm going to write this as a fact. If the function f is equal to some other function g for all x around a, so for all x in some interval a minus h to a union a to a plus h, for some positive h, then limit as x approaches a of the function is the same as the limit as x approaches a of the function g. If around the point A, if two functions are equal, then they behave in the same way, so they have the same limit.
Can you repeat?
If around the limit point A, around, not at, but around the point A, if two functions are equal, then their limits are equal. Like in example 3, we have the function f and the function x plus 2. For every x different from 3, f of x is equal to x plus 2. So for the limit at 3 of f is the same as limit of x plus 2. Okay?
Can I ask a question?
Go ahead.
Why does h have to be greater than 0?
Because if h is less than 0, then the interval a minus h to a doesn't make sense.
Okay, thank you.
Later, when we discuss derivatives, in the limit, we are going to use h again, and in that limit, h can be both negative and positive. It is customary for a positive number, it is customary to use epsilon, but I didn't want to scare you from the beginning. Maybe you heard the stories of epsilon delta definition of the limit. So any positive number, maybe I could have used r. Doesn't matter, it's just a name, but in order to talk about the interval from a minus h to a minus h must be less than a, so the number h has to be positive. Any other questions? Example 4. So in the same spirit, for this number h, as long as it is positive, it works. Even if it is too small, like if you have the function f defined to be the constant 2, if x is between minus 1 over 10 to the 10 and 1 over 10 to the 10. And it is defined to be 1 if x is less than or equal to minus 1 over 10 to the 10, or x is greater than or equal to 1 over 10 to the 10. 1 over 10 to the 10 is a very small number, but it is positive. It is a positive number. It is not 0. All right. So the limit as x goes to 0 of the function f around zero, in a very small, but still on some interval around 0, the function is defined to be the constant 2. So the limit of the function is the same as the limit of the constant 2, so the limit is 2. When you're sketching this graph, using a software on your computer, maybe 10 to the 10. I don't know how many digits. It depends on how good a computer you're using. But if the number gets too small, computers cannot distinguish between a very small number and 0. So on the graph, you may not be able to see this behavior of the function, okay? But still, the number is this interval, although it's very small, it is an interval. So the limit of the function at 0 is equal to 2. Okay? Any questions? So for the graph of this function, it depends on your scale, of course. When I'm sketching the graph, I can scale in any way I want. So I can say, here is -1/10 to the 10. Of course, my scaling on the x interval is quite different than the scale on the y-axis, but when I'm drawing, I can scale as in any way I want. So this is the point. If you read the book, you see that the book tries to make this point. When you're sketching graphs using a software, it is important that you understand the behavior yourself so that you can give the proper commands. Like you need to arrange the x interval, you need to arrange the y interval in order to see the complete picture. So you need to think about the function yourself and write the information accordingly. Otherwise, you will not be able to see the whole behavior of the function. Okay, so relying on technology is not enough. You need to also rely on yourself. All right, now before we consider other examples, let me give you the properties of limits as a theorem. I prefer the word property because, okay, the book says limit rules. When you say rules, it sounds like somebody imposed those rules. These are the rules the limits must obey. But no, these are not imposed rules. These are properties which are coming from the definition of the limit, not some, someone from somewhere else imposing the rules. So that's, I prefer using properties, but they're also known as limit rules. So let the limit of some function f as x approaches a is L, the number L. Of course, when we say the limit is a number, we mean a real number. Remember that infinity is not a number, okay? Limit as x approaches a of the function g is the number m, again, real number. And let k be a constant. Then, if you look at the limit of the sum of the two functions, f plus g, this is the sum of the limits, L plus m. And if you look at the limit of the difference, f of x minus g of x, it is L minus m. If you look at the product, f times g, the limit is L times m. If you look at the ratio, f over g, limit is L over M, provided that the limit M, of course, is not 0. You can also take f of x to a power. Wait, where is my times? Okay. First, okay. Let's consider. You can multiply your function as a special case of property 3 if you multiply your function with a constant. As I said, you can think of it as special case of property 3, limit of the constant k, limit of the function f, and limit of the constant k is again the constant k. So this is k times L. Now, if you take the function to a power, to a certain power, at the moment, we don't know, we haven't defined yet. Later, we are going to define exponential functions, but at the moment, we don't know how to take any real power. We know only how to take rational powers. So I'm going to take a rational power, m over n, m and integers. If you take a rational power, it is L to the m over n, but of course here there may be a problem. If L, the number L is negative, and if the rational power involves an even root, the number is not defined. So I'm going to say the limit is L to the m over m if L to the m over n is defined. And m over n, I mean a rational number. Maybe we didn't talk about this, but what do we mean by taking a number L to the power m over n? It is the nth root of L to the power m. Oops. And another thing, the limit respects the order. So if one function, if the function f is less than or equal to the function g, I'm going to use my interval with h again, for all x in a minus h to a union a to a plus h for some positive h, then the limit of f is less than or equal to limit of g. The only thing you have to be careful of here in the order business, even if f of x is strictly less than the function g of x, we have the limits might be equal. So for the limit, you should say less than or equal to, even if the function f is strictly less than g, like, for example, you may have, this is g, and this is f, this is a, this is L. So in this picture, for x different from a, the function f is strictly less than the function g, but they have the same limit. So it is possible that although one function is strictly less than the other, around the point A, they may still have the same limit. So we should, in the limit, we should use less than or equal to. So now, using these properties, we can figure out some other limits. Example 5, I guess I continue with. So example 5, the limit as x approaches -3 of x squared minus 9 divided by x squared plus x minus 6. So we notice that the point, the value x equals -3 makes the denominator 0, so it's not in the domain, but it also makes the numerator 0. And since both the numerator and denominator are polynomials, it says that we can factor out, since at -3, the polynomial is 0, it means we have the factor x plus 3. And the numerator we can factor out as x plus 3, x minus 3. And the denominator we factor out as x plus 3, x minus 2. So since we are taking the limit at -3, it means we are looking around -3. So x is not equal to -3. Okay, the point -3 itself has nothing to do with the limit. So we can safely simplify x plus 3. This ratio, x squared minus 9 over x squared plus x minus 6, is equal to the ratio x minus 3 over x minus 2 for all x different from -3. So they have the same limit. And now the numerator, limit of x is -3, limit of the constant is -3. By property 1, you can add the limits. So limit of the numerator is -6. And similarly, the limit of the denominator is -5. So by property number, whatever, our limit is 6 over 5. Now, I'd like to point out one thing. When you are working out your limit, you're factoring out, you're rewriting your function in some way, in all the steps, you have to include this limit notation. We are taking the limit, and after we take the limit, once you take the limit, then you don't write the limit anymore. So these two, I'm saying this because you in the exam, you need to write down your solution correctly. So something like this would be wrong. This is something we see a lot on papers. Or this is again not true. The limit itself is 6 over 5. Well, okay. It is true, but not in this order. You need to say, you can say the limit of this function is equal to 6 over 5. 6 over 5 is also the limit of the constant. Therefore, the limit of x minus 3 over x minus 2 is equal to the limit of 6 over 5, but not in this order. This would be wrong. Once you take the limit, you don't write the limit anymore. Any questions about this?
Can you just explain what is one set of way that we can write that we can follow? That's like the most appropriate one. So we follow that.
Yeah. This is how I write. This is the correct way of writing it. But again, you know, when you're writing it down, you need to think about what you're writing down. If you're writing down this, on this side, I'm taking the limit. But on this side, there is no limit sign. So how can they be equal? You should always think when you're writing down. I know when you work on, you know, enough number of problems, it just becomes automatic. You just keep writing without thinking about it. But in the beginning, maybe you should write down your solution and try to criticize yourself. Think about every equality. Is it really true? What did I use here? Am I right? You know, does it make sense? Any other questions about this? Okay. Yes, we are using symbols. We are writing down formulas, but whatever you wrote down, you should be able to read as a complete and correct sentence. When I write down, I read it as limit as x goes to -3 of x squared minus 9 over x squared plus x minus 6 is equal to the limit as x goes to -3 of, and so on. So it is a sentence. What you wrote down in formulas, you should be able to read as a sentence. If you don't write the limit part, then you cannot read the limit. When you read it, if you don't have this limit right here, I cannot read it as the limit. I read this as, I read this as limit as x goes to -3 of x squared minus 9 over x squared plus x minus 6 is equal to x minus 3 over x minus 2. Something wrong, right? Okay, so example 6, one of my favorite examples. Limit as x approaches 2 of absolute value of 2x minus 5 minus absolute value of x minus 1 over. You see limits in high school, right? No, but in the exam there are questions in the entrance exam. No limit questions. Kaç
They spread.
üniversite sınavında?
Normally, yes, but normally, yes, not in our year because of the pandemic.
I see. Yes. Okay. You were not responsible for the for that year. Yes. Okay.
For the same reason they scrapped derivatives and integrals.
Yes. Okay. Yeah. I see. So if you have questions, then if I'm going too fast, don't hesitate to stop me and ask, please. So am I going too fast? Maybe. Okay. Now this is funny. Now I'm making fun of myself. Okay, now I know that if you don't just get it, it is hard to ask questions. I understand that. In order, there's a question. L to the m over n. L to the m over m. For example, -2 to the 1/2 is not defined. It sure is. That's what I meant. When you take an even root of a negative number, it is not defined. But minus 2 to the power 1/3 is defined. Okay, that's what I meant. So as I was saying, I know that it is hard to ask questions when you don't understand. So you need to, okay, for the limit, the concept of limit is the hardest concept of this whole calculus thing, the hardest one. So if you don't just get it, don't be hard on yourself, okay? It needs some, so first try to go through the motions. How do I find the limit? Try to look at, I try to solve many different types of examples. So try to look at my examples, try to look at the examples in the book, in other books, some solved problems. I'm sure that you have lots of resources. And then by looking at how they work it out, try to work out a limit yourself. But you need to work on it, okay? Don't put it under your bed or something. You need to keep working at it. And then you will start having questions, and you can ask me your questions anytime you want. Okay, so for this limit, again, both the numerator and the denominator at the point x equals 2 is 0. But how to work it out? Because in the numerator, we have absolute value. But in the first absolute value, at x equals 2, 2x minus 5 is minus 1. So it says around the point 2, 2x minus 5 is negative, okay? So 2x minus 5, it is 0 at 5/2. So here is 2, here is 5/2. And the second absolute value, x minus 1, is 0 at x equals 1. Let's say this is 0. So around the point 2, maybe I can take, it doesn't, I'm always taking a symmetric interval, but it doesn't have to be symmetric, but just to. So we can consider this interval for x in the interval 3/2, 5/2. Since x is less than 5/2, 2x minus 5 is less than 0. And since x is greater than 3/2, x minus 1 is positive. X minus 1, in fact, x is less than 3/2, so x minus 1, x is greater than 3/2, so x minus 1 is greater than 1/2, so it is positive. All right, so absolute value of 2x minus 5 is minus 2x minus 5, and absolute value of x minus 1 is x minus 1. This is for x in the interval 3/2, 5/2. And remember, if two functions are equal around the limit point, they have the same limit. So for the limit, I can replace for this limit as x goes to 2 of, what did I write? Absolute value of 2x minus 5 minus absolute value of x minus 1 divided by x minus 2. I can replace my function absolute value of 2x minus 5 with minus 2x minus 5 and absolute value of x minus 1 with x minus 1. So minus 2x minus x minus 3x plus 5 plus 1 plus 6. Okay. Let me finish the limit and then I will come back to this discussion, okay? Then we, in the numerator, we factor out minus 3. So we have x minus 2. And now, again, around x minus 2, this function is equal to the constant minus 3. I keep the limit here because I'm canceling out x minus 2. So around x equals 2, the function is equal to the constant minus 3. And the limit of the constant is the constant. Okay, so what I'm trying to do is I have absolute value of 2x minus 5. So in order to be able to evaluate the limit, I have to get rid of this absolute value. In this interval, if I take x between 3/2 and 5/2, x minus 1 is greater than 1/2, right?
Why did we choose this interval?
Why did we choose this interval? I like the number 1/2. Okay, why did we choose this interval? In the absolute value of 2x minus 5, 2x minus 5, all right, maybe I should give more detail here. Oops. Yeah, okay, so I have absolute value of 2x minus 5. It is 2x minus 5 if 2x minus 5 greater than or equal to 0, and it is minus 2x minus 5 if 2x minus 5 is less than 0. This is the definition of the absolute value. Okay, now 2x minus 5, here, if I work out this inequality, I have x greater than or equal to 5/2. And here I have x less than 5/2. And for the other one, absolute value of x minus 1 is equal to x minus 1 if x minus 1 greater than or equal to 0, meaning if x is greater than or equal to 1, and it is minus x minus 1 if x is less than 1. Okay, now, so for the first absolute value, the breaking point is 5/2. And for the second absolute value, the breaking point is 1. And I'm looking at the limit at 2. Okay, so I need to take the interval which includes 2 or around the point 2. So for the first absolute value, I need to consider x less than 5/2. And for the second absolute value, I need to consider x greater than or equal to 1. So to be precise, I need to consider this interval. Instead of taking 3/2 to 5/2, you can take from 1 to 5/2. I cannot go beyond 5/2 because beyond 5/2, absolute value of 2x minus 5 changes its behavior. In all the above discussions, I give you a symmetric interval, a minus h to a to a plus h. In order to be symmetric, on the left, on the right, I go up to 5/2. So on the left, this is 1/2. So if you take 1/2 on this side, you get 3/2. That's all. just to be symmetric. But you don't have to be symmetric. You can take the interval instead of, oh, I need to give a break. Instead of 3/2, 5/2, we can consider, we can take 1 to 5/2. That's also fun.
Isn't one included in the brackets?
You can, but okay. But in the definition, I give you open intervals, so I need to take the open interval here.
Teacher, can I ask something?
Sure.
Can we choose a point near to 2 rather than finding the interval, such as like 2 plus h? H is so small number, so we can compare to abstract values, and we can find the symbol of them. For example, -2x, -5.
Yes, this is what I'm doing. By the way, I'm going to give a break, so if you don't have any questions, you can, take your break now. I'm going to give a break of 10 minutes. This is what we are doing, really. Okay, remember I defined the interval a minus h, a minus h, a plus h. This is what we are doing, taking the value of x near a, and this number h here can be a very small number. You don't have to take, in this example, you don't have to take 5/2. You can also take, you can take 1.98, 2.01. Any small interval around 2.
Thank you, I get it.
I have a question.
Sure.
How will the absolute value change if the 5/2, or if the interval is greater than 5/2? Change its properties, I mean.
Because in general, remember, absolute value of x remember the definition of the absolute value. It is x if x is greater than or equal to 0, and minus x if x is less than 0. This is the definition of the absolute value. So absolute value of 2x minus 5 then is equal to 2x minus 5 if 2x minus 5 greater than or equal to 0, meaning x greater than or equal to 5/2. And minus 2x minus 5 if x is less than 5/2. Because at 5/2, 2x minus 5 is 0. It's because of the definition of the absolute value.
So we can't include in the interval x greater than or equal 5/2.
Okay, now for the function, the absolute value of 2x minus 5, of course, it is also defined for x greater than or equal to 5/2. But as your interval around the point 2, we are taking the limit at 2. Okay, we are taking the limit at 2. If you take as your interval, of course, you don't have to take 2 itself. Let's say you go up to 3. Here is 5/2. So if you consider, for example, x between, let's say, 1 and 3. For x between 1 and 3, absolute value of 2x minus 5 changes the behavior. I do not need to consider x greater than or equal to 5/2 because the limit, I'm looking at the limit at 2. So I need to look at an interval which contains 2. Because 2 is not greater than or equal to 5/2.
Oh, okay, now I get it.
Okay, since we are looking at limit at 2.
Can I ask another question?
Sure.
In the exam, if we can we write the answer and steps in a few steps instead of writing the whole?
Oh, okay. For the exam, what?
Because some
okay.
questions could be very easy to solve.
Okay, so for the exam, you can say limit. Okay, this is what we have. X goes to 2. You can say this is the limit minus 2x minus 5 minus x minus 1 over x minus 2. You need to write some kind of an explanation because near x equals 2, 2x minus 5 is negative and absolute value of 2x minus 5 is minus 2x minus 5. And x minus 1 is positive, a lot of n's. I should use maybe here, and absolute value of x minus 1 is equal to x minus 1.
And we have to write explanations
Yes,
for
yes.
everything.
Yeah, every equation you need to give your reasoning. Why did you take this limit equal to this limit?
Okay.
But you don't have to give specific intervals, like take x between 3/2, 5/2. You can just say near x equals 2, 2x minus 5 is negative, and x minus 1 is positive. You need to write that down, yes. Okay, then let me just take a 5 minutes break, okay? And then I'll be back. Are there any other questions? All right, now let me give you another example involving the absolute value. This was example 6, so example 7. Limit as x approaches 0 of absolute value of x divided by x. Again, we have absolute value. So to be able to evaluate the limit, we have to resolve this absolute value. But absolute value of x depends whether x is greater than 0 or less than 0. Now, for x greater than 0, greater than or equal to 0, absolute value of x is equal to x, and absolute value of x over x is 1. And for x less than 0, absolute value of x is minus x, and absolute value of x over x is -1. So this function, absolute value of x over x, is constant -1 if x is less than 0, and constant +1 if x is greater than or greater than 0. Because I cannot include 0 because I'm dividing with x. So the denominator cannot be 0. So I cannot include 0 itself. If x is greater than 0, it is 1. If x is less than 0, it is -1. By the way, this function has a special name. It is called the signum function. And it is denoted by SGN of x, signum, or just sign function. For positive numbers, +1, negative numbers, -1. So the sign function, it depends on the sign of x. So when you consider the picture, the graph, this is the graph. All right. So for x near 0, if x is greater than 0, f of x is constant 1, and if x less than 0, f of x is constant -1. So there is no fixed value where the function values approaches to. On one side it is +1, on the other side is -1. So the limit here, we say that this limit does not exist. There is no such limit, does not exist. Okay, there's no fixed value for the limit at x as x approaches 0. If you approach 0 from right, the function is constant 1, but you approach 0 from left, the function is constant -1. So there is no limit.
Is it an odd function?
One moment.
Are we supposed to write in submatrix exams?
Yeah. Yeah, so you just write does not exist. Yes.
Is the function odd function?
Odd function. Yes. Yes, signum function is an odd function.
May I ask a question?
Sure.
Is the mean of sine function is limit of the function does not exist, or another meaning?
Oh, the sine function is a function by itself. It's a special function, like the square root function, absolute value function. It has a special name. Okay.
Okay, I see. Thank you.
Its limit at 0 doesn't exist. It is not defined at 0. 0 doesn't belong to the domain. The signum function is only defined for non-zero numbers. Okay, so this is the definitions. It is not only for this example. In general, we have the signum function. The definition is it is -1 if x is less than 0, and +1 if x is greater than 0. But instead of writing partially like this, you can also say it is absolute value of x over x, or x over absolute value of x. They're all the same thing. Whichever you prefer. Any other questions? And it's an odd function. Signum x is an odd function. Now, this behavior, approaching from right and approaching from left, this may occur in other cases. So instead of writing down the reasoning with sentences like this, again, we have a special way to denote this behavior. If you are approaching only from the right, then we call it the right limit. And if you approach it from the left, we call it the left limit. So one-sided limits. Okay. If x approaches a through values greater than a, then we say the right limit, right as the direction, right, left, right limit, and right limit as x approaches a, right we denote by the plus sign of f. Okay. If x approaches a through values less than a, we say the left limit and right, the left we denote by minus sign. Limit x approaches a from left. So in above example, as x approaches 0 from right of absolute value of x over x, as you approach from right, it means x is positive, so absolute value of x is x. So we cancel out x and x, we have constant 1, so the right limit is 1. And if you approach from 0 from left, x is less than 0, so absolute value of x is minus x. So x, when you cancel out x, you have the constant minus 1. So the left limit is minus 1.
So the limit would have a value if it was specified whether it's in a right limit or a left limit.
Yes, yes. So if the right limit turns out to be different from the left limit, it means there is no limit value. Okay, so since limit as x approaches 0 from right of this is not equal to limit as x approaches 0 from left, the limit itself, and instead of writing does not exist, we usually write d dot n dot e. It is not a proper notation, of course, but means does not exist.
I believe this is what we call continuity, as like not having a two-sided limit. I guess this is what's called continuity, as having a two-sided limit.
Continuity, it means this is an example where the function is not continuous, but it is not the only case. So this is not the definition of being continuous or not continuous.
I understand.
It is a case where the function is not continuous, but there are other situations. not only right and left limit.
I understand.
Okay, so of course, I'm doing all this intuitively, so things come out to be like natural. Yes, right limit different from left limit, so limit doesn't exist. All of this have a precise definition, and what we feel to be true intuitively is actually true, but I try to write it as a theorem. So with the precise definitions, you can prove this, that this is true. The limit as x approaches a of a function f is the number L if and only if the right limit is this number and also the left limit is this number. So if the right limit or left limit doesn't exist, or if they both exist, like in this example, but different, then we say that the limit of the function doesn't exist. On the other hand, if the right limit and the left limit turn out to be the same number, then we say the limit is that number. For example, okay, let me give you a couple of examples. Examples. Consider this function. It is defined to be x squared plus 1 if x is greater than or equal to 1, and 3x if x is, if x is less than or equal to 1. And 3x if x is greater than 1. Now, if you try to find the limit of this function as x approaches 1, since the function is defined differently on the right and on the left of x equals 1, we need to check the right limit and the left limit. If we are looking at the right limit, x approaches 1 from right, it means x is greater than 1. And when x is greater than 1, the function is given as 3x. So the limit, the right limit is 3. And when you're checking the left limit, now x is less than 1. When x is less than 1, the function is defined to be x squared plus 1. So the left limit is equal to 2. So since the right limit of the function at 1 is not equal to the left limit of the function, the limit at 1 does not exist. So the picture of the function it is x squared plus 1 for x less than or equal to 1, and 3x and 3x for x greater than 1. So the right limit is 3, left limit is 2. The function doesn't have a limit at x equals 1. On the other hand, if you have a function Any questions about this example? On the other hand, if you have a function defined to be x squared plus 1 if x is less than 1, 3 if x is equal to 1, and 3x minus 1 if x is greater than 1. Now, again, since the function is defined differently on the right and left of x equals 1, to check the limit at 1, we need to check the right and left limits. For the right limit, x is greater than 1. When x is greater than 1, the function is defined to be 3x minus 1. So the limit is 2. And the left limit, when x is less than 1, the function is defined to be x squared plus 1. So the left limit is also 2. So this tells us that the limit of the function as x goes to 1 is equal to 2. So if the right limit and left limit turns out to be the same number, then that number is our limit. And the graph of this function x squared plus 1 and 3x minus 1. And at the point 1, it is defined to be 3, but of course, this value has nothing to do with the limit. The right limit and the left limit, they are both equal to 2. So the limit of the function is 2.
Limit of a function looks, investigates the movement of the function around a given value, not the value itself.
Yes, exactly. Not the value itself, but what happens around that value. Any questions about this? Now, we have another very important and very powerful tool for evaluating limits. Again, I'm hitting the wrong arrow. It is called squeeze theorem or sandwich. Sometimes it's called property. It is a property. It can be proved using, again, the precise definition of the limit. Okay, so basically what it says is that if your function is squeezed between two functions, so if your function f is squeezed between two functions, g and h, around A again, so I'm going to write my usual sentence for all x in A minus HA, union A plus H, for some positive H. And the limit of the function g at the point A, some number L, exists and is equal to the limit of the function h. So your function is squeezed between two functions and the function sequencing or sandwiching your function in between have the same limit at x equals a. Then, in this case, the function which is squeezed in the middle must have the same limit. Then, the limit as x approaches a of the function f is equal to the same limit f. So at the point A, you have some function so this is h of x, this is g of x, and your function is squeezed in between. And let's say they all have the same limit, h and g, then your function must, in the middle, must have the same limit. Does it make sense?
Yes, but
Hmm.
I'll have to ask a question. So let's say the limit of g and h in the point of A is not equal, but the first condition still applies, like g smaller than f, f is smaller than h.
Anything can happen.
There's no one rule about that.
Yeah, there is no conclusion you can draw. If the limits of G and H are not the same, F can be anything. So like, I will try to answer this pictorially. So at the point A, let's say this is your H, and this is your G. The limits are not the same, so F may be in between, it can do any kind of crazy things. It doesn't has to have a limit, and even if it has a limit, it may, the function in between may have a limit, but it can be any number between these two. What you can say is, now if G, F, H, and if they all have limits, then we can say that the limit of G is less than or equal to the limit of F. It has to be, if the limit exists, it has to be between the limits of G and H. But the limit may not exist.
If limits exist, then limits sandwich this, but between
Yeah.
these values,
Yeah, if it exists.
if it exists.
If it exists, if it may not exist, like in this picture, I
Anything
tried
can
to draw
happen.
here. The limit of f may not exist. Just because it is sandwiched between two functions, which has a limit at a, doesn't guarantee that f itself has a limit. The sandwiching functions must have the same limit at
For
the-
all three functions, Okay.
Excuse me, I think you wrote g of x instead of h of x in the last expression.
I'm sorry, what, I don't understand the question.
I think you wrote something wrong in the last expression. Limit
G, F, H, yes, it has, this should be H. Yes, thank you. Is this what you meant?
yes, exactly.
Okay. In order to talk about, any, no, okay, I know, it's not true. All right, let me give you an example. For example, suppose your function is between the functions 1 minus x squared and 1 plus x squared for all x. O arada koca yer boşluk bırakmışım. Hay Allah. Neyse. Ne oluyor? Okay, so suppose your function is between the functions 1 minus x squared and 1 plus x squared. About the limit at 0, the limit as x approaches 0 of the function 1 minus x squared is 1. And also the limit as x approaches 0 of 1 plus x squared is also 1. So we can conclude that the limit as x approaches 0 of the function f is equal to 1. But, for example, we cannot say anything. Okay, or we can say something. But, for example, the limit as x approaches 1 of the function f may or may not exist. Just because it is between 1 minus x squared and 1 plus x squared, because the limit as x approaches 1 of 1 minus x squared is 0, and the limit as x approaches 1 of 1 plus x squared is 2. The only thing we can say, is if the limit as x goes to 1 of the function f is the number L, if this number exists, then it has to be a number between 0 and 2. That's the only thing we can say. If it exists, it must be a number between 0 and 2. But it may not exist, or even if it exists, it can be any number between 0 and 2. Just using this information, that the graph is between the graphs of 1 minus x and 1 plus x. I said 1 minus x squared, so minus x squared plus 1, so 0, 1, and I have one parabola and the other parabola like this. So my function f at the point 0, the limit has to be 1, but at other points we cannot say it. All right, so this is where I want to talk about trigonometric functions, but should I start? Do you need to go to another class? Okay. I'll stop now. It is 10:20. We are supposed to stop at 10:20. So I will. Is it okay if I record a video about definition of trigonometric functions and you watch the video before next class?
Will it be uploaded in Auto class?
Yes, yes.
Okay.
Okay, then that's
That's
what I'm
fine.
going to do today.
Will we go over the video in the upcoming session?
Well, yeah, it's some, basic points, but it would be very good if you watch the video before next class. I will try to do it today. So tonight it will be available for you. Okay?
Okay.
Oh, questions? Can we join your class in the classroom? Yes, you need to send me, if you want to come here to the classroom, you need to send me an email together with your HES code, okay? And then if there are, I can only take 14 students at a time. If there are more than 14, then I'm going to rotate.
Can I
Can
ask a
you
question?
explain again? I can't understand. Can you explain again?
If you want to join me here in the classroom physically, when I'm lecturing, you need to send me an email with your HES code. I can only allow 14 students at a time. If there are more than 14, then I will have to rotate you. Some of you are going to come on Mondays, some of you will come on Wednesdays. But first you need to, if you want to come to the classroom, you need to send me an email. Is that clear?
We just write, I want to join with you and just HES code, just it.
Mhm.
Okay, I see.
Can I ask another question?
Sure, go ahead.
Do the ones who have sent you email before have to need to send email again to join club session in the classroom?
Oh, if you already send me an email, you don't have to send it again.
But I sent it last week.
Oh, okay. So did you come to class last Wednesday?
Yeah,
Oh, okay.
how's that?
Yeah, you don't need to. You don't need to send
Okay.
it again.
Okay, thanks.
Mhm. Yes, but the end of the chapter, the precise definition of limit at the end of the chapter. I'm sorry, I couldn't read all the chat. Are there any other questions I didn't answer? Please write it again. I didn't read the whole chat. I tried, but. Oh, okay. Yeah, you said okay. All right, good. You too. All right, so for trigonometric functions, I will record the video. Now I stop the video.